The purpose of Lab 5 rope swing is to explore and apply previously learned concepts to a topic of interest. I choose to analyze the motion of an oscillating mass, specifically a person's swing on a rope, to determine whether or not total energy is conserved in a closed system and to compare tension versus gravitational force. To do this, we will obtain observed position data from Tracker and use GlowScript to model how the different types of energy and forces change and compare with one another. From this lab, we gain more experience with spring potential energy, spring force, gravitational potential energy, gravitational force, and kinetic energy. And ultimately, we conclude that total energy is conserved when the tension force felt by the person is greater than the person's weight. The fundamental principles examined in this lab are Newton's first law, Newton's second law, and the energy principle. Newton's first law is essentially inertia and states that an object at rest will stay at rest, and an object in motion will stay in motion if no external force is applied. Newton's second law is F equals ma, which can be derived into the velocity update formula and position update formula, and these derivations will be used in the theoretical model to generate data points for the object's motion. The conservation of energy essentially states that in a closed system, even though energy may change forms, the total amount of energy will stay the same. Now this is the data I obtained from Tracker, and if we see here, this is a video of the man falling as he swings from the rope. Now, as you can see in my data, I only track the first half of his swing down to his lowest point because I'm unable to accurately track the height in the following trajectory of his swing because of the video. Now, continue on to some assumptions that I had to make for GlowScript. So because it was a man in the video, I did assume that his mass is about 80 kilograms and that his height is 5.6, which are the average statistics for a man. And also because he starts from rest, the initial velocity is 0, 0, 0. And the initial position we obtain from Tracker, which is the numbers shown on the screen. And also we know that the rope is 45.72 meters long, so we can set that equal to L naught. And then I'm also able to calculate K constant using the equation listed there on the slide, which involves tracking the amount of time it takes for him to complete one oscillation as well as his mass. Now moving forward into coding, we begin by changing the initial conditions and as well as inserting the velocity update and position update formulas. And after that, we define some key constants such as the gravitational constant and spring constant, as well as the relaxed length of the spring, which is L naught. And then we also define our different types of energies. So that includes kinetic energy, gravitational potential, spring potential, and then the total energy. Now after this, we head into our calculations. So we define the initial energies here, and then we insert the equations to calculate gravitational force, spring force, and net force. And then we also update the velocity and position, and we also update the spring, and ultimately we calculate the energy changes. And after this, a section is added in to graph the arrows for F spring and F grav to see how they compare to one another in terms of magnitude. Now after all this, the following visuals appear. So on the left side of the screen, you're going to see that the orange arrow is my arrow for F spring, and the magenta arrow is my arrow for F grav. And as you can see, the magnitude for F spring is much greater than that for F grav, and that is going to match up with our mathematical calculations, which we will look at later. Now on the right side of the screen, on the top side of the right screen, we see the four types of energy. We have kinetic energy, gravitational potential energy, and spring potential energy. And then our total energy is marked by that orange line. So as you can see, total energy is roughly conserved, or the change in total energy is roughly 0. So that does tell us that energy is roughly conserved throughout the whole process. And then at the bottom right hand corner, we track the position, specifically the Y position of the man as he falls for one oscillation almost. So some sources of error in My model are definitely human error while inputting point mass in tracker, and then also my model does not take into account air resistance, and also I did have to make some assumptions when creating my glow script code, including the mass and the height of the man. In order to help mediate these, we can add more data points to make the curve smoother and more accurate, as well as obtain some more detailed data from the people who made the video to see the more specific numbers for the mass and height of the man. Now, after this, I was curious to see how mathematically the magnitude of tension and spring would line up, as well as the maximum velocity. So on the left, we have maximum tension, and on the right, we have maximum velocity, which we find to be 27.868 meters per second, and then we find that the magnitude of tension should be about 3 times the gravitational of the man. All right, thank you.